Okay, go ahead and start. All right, today we want to look at Coulomb's law again, right?
Yeah.
So let's say we have the charge here. We'll call that charge Q naught. And then we have two charges, Q1, Q2. Right, and we want, let's, for simplicity, we'll assume they're positive, but it could be positive and negative. Okay? And we want to calculate the force on our little charge Q naught. So little Q naught is kind of like a test charge. It's like a little tiny charge, and I'm just feeling the force created by Q1 and Q2. Does that make sense to everybody? So we know that there would be a force from here going that way. We'll call that F1, and there'd be a force over here this way, F2, and we would add those forces to get the total force on my test charge, right? So the total force would be the force from the first charge plus the force from the second charge. We use Coulomb's law. We can write that out as K Q naught Q1 over R1 squared R1 hat plus K Q naught Q2 over R2 squared R2 hat. This would be R1. This is R2, right? Does that make sense to everybody? Yes?
Is this assuming that like they're all positive forces?
Yeah, right. They could be positive or negative. I'm just making the picture they're positive.
Okay.
But in the formula, they could be positive or negative, right? I'm just trying to make it simple. So you see, I've got some similar terms here in these two things. I got a K and a Q naught. I'm going to factor out a Q naught and then leave what's behind. So I could write this as Q naught times K Q1 over R1 squared R1 hat plus K Q2 over R2 squared R2 hat. Right, I just factored out the Q naught. And this little Q naught's like my test charge. And you could imagine, I could move this test charge around. I have a little test charge, but I don't have to leave it there. I can put it here, or over here, or there, or there. I can move this test charge around, and if I did that, I would get the force in all these different places. Yes, Matthew?
Can you not also pull out the K?
I could, but I want to leave it in,
Okay.
and you'll see why in a minute, but you could pull out the K. All right? So, mapping this around, notice this whole thing, this thing in here, right, doesn't depend on my test charge. All right? So we're going to introduce a new concept with this called the electric field. And this electric field is going to exist around a charge. And the force on a test charge, or a force on any charge, would be the charge times the electric field. So this here is the electric field created by these two charges, Q1 and Q2. Okay, so we're entering some new ideas here. Okay? So we're going from vectors to vector fields now. Right, we're introducing this field concept. And this field exists through all of space, created by these charges. Right? So what's the formula for the electric field for a charge? And actually, I'm going to put a parenthesis R here because it's a function of position. It's going to be KQ R squared R hat. That's how we can calculate the electric field from a charge. Okay? So this charge is making an electric field. This charge is making an electric field. I add those electric fields and I get a total electric field, and then I can measure the force from that electric field by putting in a test charge. Okay. I need two charges to have a force, but a single charge will create a field by itself. Right? Does that kind of make sense?
Let's say it again.
I need two charges for a force.
Why?
Because force is the product, right? The Coulomb's force is K Q1
Okay.
Q2 over R squared. I have to have two charges interacting to get a force. But a single charge by itself will create an electric field. Okay?
Why do you need two charges, but other than that's the formula?
Well, because force is a push or pull between two objects.
Okay.
Right? And if I just have one object, I don't have a push
And
or a
then
pull.
there's nothing's acting on it.
Right. But I still have the field. This is field like Star Wars. Anybody ever seen Star Wars or Star Trek? And they have their force fields. Activate the fields, right? This is a real field. They've taken that idea from this idea. Right? But they don't quite do it right. In
So
this.
essentially, the force can also be like defined as two fields interacting with each other.
Well, the fields add. Right? The fields can add. So they add up. They don't really interact. They just, it's called superposition. They add on top of each other.
But they can also subtract, right?
And they can also, well, right, well, because they're vector fields, so they can point in different directions. So this is a vector field. It's like a vector, but it's a vector that has a value everywhere in space, and it's not at one spot. Okay, so we draw it a little different. Okay, let's see how we draw vector fields. Jerry, you're much better at erasing than I am.
Well, it took a long time.
So, we're going to look at a single positive charge in space. So here's my positive charge Q. It's positive. And it's going to create a field around it. I'm going to try to draw this as best I can, but I don't always draw everything perfect. But this field, this electric field exists in space, and it's kind of like spokes on a tire. It's spreading out like this, right? And it's spreading out like that. But you got to think 3 dimensions, not 2. I can only draw 2 dimensions. Do you know what a koosh ball is? Those like rubber band balls that you cut and then all the rubber bands stick out. No. That was a big thing when I was a kid. Koosh balls. A pin cushion, you know what a pin cushion is, right? And all the pins are sticking out all different directions. That's what's going on, but I'm just drawing in 2 dimensions, right? But these field lines are going out in all directions, pointing out from each other.
What's inside this?
That's the positive charge, Q.
Oh,
So it's positive, it's charge Q, and that's the charge, and it creates its electric field around it. So this is the electric field. Now, normally we represent vectors, their magnitude by their length, right? That's not the case with fields though, because these lines just keep going on forever. So I can't use length. So what we do is we use the density of lines. The closer the lines are together, the stronger the field. So in here, where's my black marker? In this area here, the lines are closer together, the field is stronger. Out here, the lines are further apart, so the field is weaker. Does that make sense to you guys? Okay. A negative charge looks pretty similar. I'll draw a negative charge over here. Negative Q. But the field lines come into a negative charge. Like that. So, we can think of this as positive charges as sources of electric fields, and negative charges as sinks. Electric fields go into the negative charge.
That's what?
A sink, like a drain,
Mm.
right? So you got the source, the electric field flows out of the positive charge, and flows into the negative charge. Okay, so this is the electric field around my negative charge. Okay, and these fields exist through space.
You said that's a sink, that's a what?
That's a source, that's a sink. Or a faucet and drain, but we call them source and sink. Okay? If I make the charge bigger, so let's say I went from Q to 2Q, right, I doubled the charge, I would double the number of lines. So if I have 1, 2, 3, 4, 5, 6, 7, 8, I would need 8 more lines if I went to 2Q. 1, I should have 16. I don't know how many I have. But right, the more charge, the more lines. The stronger the field. Right? Yes?
What does that look like on a molecular level?
Like that.
Yeah, but like, so like say you have.
So you have a proton.
Like, okay, so say you have potassium and calcium.
Yeah.
Right, I think that's a 1A, 2A. So that would have a positive 1 charge, whereas a two positive charge would have.
We're gonna have more lines. Yeah.
Lines.
Mm-hmm.
Okay.
Yeah. Okay. So this is the electric field. Now what's interesting is when I bring an electric, one charge next to another charge. These field lines, they do some interesting stuff. But mathematically, you just add fields. So the total field, E total, is just the sum of the individual fields. Right? And this is a function of R. Right, so I just add them up. So mathematically, I just add them. But the pictures are interesting, how you draw the pictures. Okay? So there's some rules for field lines. Are you ready for this? For drawing a field line. Rules for field. These are called field lines here. These arrows. Okay? Field lines can do some things. Well, first they come out of positive into negative. So that's kind of the first rule. Out of positive into negative. The second is that field lines can bend. So they can move. Right? They can bend with respect to each other. Third line, they can join if they're going the same direction. Right? But the fourth one, very important, and I wrote it in capital letters, field lines never cross. Now there is an exception to that, but we're not going to see it in this class.
But are they always parallel though? Or like, do they sometimes get closer?
Yeah, they can get closer, they can, yeah. So let's see what happens when I bring two positive charges next to each other. And I'll see if I can get a simulator. I should have looked that up before class, but I didn't. But let me see if I can find a simulator. Oh, this is perfect. Okay. Okay, here, perfect. This is perfect. I found a great simulator. I'll have to put this in the shell eventually, but it's coming on. Ugh, I don't really like these new boards. Just don't erase them all. Okay. Okay. So here we go. Here we have a single charge by itself. Right? That's fine. And you can see these are the field lines pointing out. We can drop some test charges and we'll see what those test charges do. So you can see the test charges feel a force, right? And they're going, notice they're going in what direction? Along the field, right? When we talk about test charges, conventionally we treat them as a little tiny positive charge, very small positive charge. When I talk about test charges, and so they're going to go in the direction of the field because light charges do what? They repel. So the test charges are being put away. Okay, let's yes.
Does the test charge itself have any, like, force?
Yes, but we're gonna treat it as so small that its effect is negligible. That's the point of a test charge. So imagine it's super tiny, but it does create its own field. But we're gonna treat it as very small. Okay, oh, there they go again. Okay, now let's try a dipole. What's a dipole? Did you learn this in chemistry? Okay, it's two charges. It's a plus charge and a minus charge. Let's see what happens with a plus charge and a minus charge. What happened to the field lines? They bent and they joined together, right? The field lines are coming out of this positive charge, but notice what they're doing. They're going into that negative charge. So the field lines have come together, joined together. Right? You see that? So the field lines were apart, and then, right? These were sticking out this way, these are coming this way, and then as you bring them together, they join up. And notice, in here, I have a very strong field in between the dipole. But out here, it's weaker. We're going to work out all the mathematics of the dipole in a minute. Okay. But this is the dipole configuration. What if I have two positive charges? Can I change these charges? Oh, I can. So let's make this two positive charges. Notice now what happens to the fields. What happens to the fields? Now instead of a positive and negative, I have two positive charges. What's going on in the fields? What are they doing? They're repelling each other. They're pushing away, right? So now they're being pushed. Oh, they can't join up because they're going the same direction. So they have to get pushed, right? So notice right here. What do you notice right there in the middle?
Empty space.
There's no field. So what does that mean the electric field is here? Zero. There's no force right there. If I put a test charge right there in the middle, it wouldn't feel a force. Right? Those aren't quite, no. Once they get on the lines, then they're going to go separate. Wait, clear test charge. What's test charge mode do? Oh, click anyway. So I'm going to add one right in the middle. See, and if you didn't get quite in the middle, it'll get pushed. So you can see there's no. Eventually, it's going to accelerate because it's hard to get it right in the middle. But you get the idea, right? So that's a positive charge and a negative charge, or two positive charges. Same thing if I had two negative charges. Or if I made this a negative charge, I'm back to the dipole pattern. There's a negative charge. Now I'm back to, right? So this is interesting. When I think about charges repelling and attracting, I can really talk about the fields, right? What makes two positive charges repel each other, or two negative charges? Well, to bring them close, I have to bend the field lines away from each other. Right, so that bending the field lines is causing the repulsion. What about a positive negative charge? Why do they pull together? Because the field lines join up. Right? And that's pulling the charges together. So combining the field lines, pulling together, is bringing the positive and negative together. The repulsion is happening by the field lines pushing against each other, and they want to straighten out. Okay, does that kind of make sense?
Has there ever, like, is it possible for the energy lines to cross, or is that just like not a thing?
Yeah, it's not. One exception, magnetic fields in a plasma, we're not going to deal with that.
Will I ever have to deal with that in undergrad?
Probably not. Unless you go into nuclear fusion or atmospheric
In
science or
undergrad?
plasma physics.
Yeah.
Then you would get a special condition.
Okay.
But yeah, no. Okay, does this make sense to everybody? These field lines? What if I have a more interesting configuration, right? Like, let's make a row of positive charges. Notice what's happening. Huh? These are starting to look right? Kind of straighter here, right? That's 3 positive charges. Let's try a dipole roll. So a roll of dipoles, plus minus charges, right? So 3 plus, or 4 plus, 4 minus charges. Notice we're getting a very strong electric field in the middle, weaker out here. Notice these lines are starting to look pretty straight in here. I'm starting to get a parallel electric fields in the middle between these 2 rows. Right? So that's kind of interesting. Let's do a random configuration. So there's a random configuration. That's what they look like. I think I can even drag these around. You can see. It's kind of a cool little program or web page. You can see all these field lines forming. All right, bring that really close, and let's put one over here. All right, and you can play around with this. That's pretty cool. So field lines, right? They're joining and reconnecting, but they're never crossing. All right, does that make sense, everybody? Okay, let's look in detail at the dipole, because the dipole is a very important pattern. A positive charge next to a negative charge, and equal and opposite charges. So this is like water, right? Did you guys talk about water in chemistry yet? H2O, it's a dipole, right? You guys, did you do that in chemistry?
I know that from other chemistry.
Yeah.
2 molecules of
O,
hydrogen.
a couple of extra electrons over here, right? This forms a dipole. This becomes a negative delta. This becomes a plus delta because it's pulling the electrons off the hydrogen. And I get a little negative charge, positive charge separation. That's what makes water do all the cool stuff it does. Like it dissolves all kinds of stuff. It gets hydrogen bonding, all that stuff, because water is a dipole. So it's really one of the most important configurations of electric fields. Okay, so we want to calculate the electric field of a dipole and see some of the consequences of it.
Is that why water conducts electricity so well?
Yeah, because it's a dipole. Well, yeah. Yeah. It's involved in that process.
Or my mom would make me get out of the pool when there's a thunderstorm.
Yeah. Bad idea. Okay. So there's my dipole pattern. Let's write down the electric field. So I got some point P here in space. Let's call this R1. Oh wait, which way did I do it in my notes? I switched these. I made that one positive, that one negative in my notes. So let me switch these around. I'm gonna make this one positive, and this one negative. Okay, that's how my notes are. So, and I wanna calculate this point here. So, R1's from the positive. So this is R2 from the negative. This is R1 from the positive. I want to find the electric field at point P. Okay, you with me? Matthew?
Yes.
All right. So the electric field at point P is a function of R. That's going to be the electric field from the positive charge plus the electric field from the negative charge. Right? That's going to be K, Q. I'll use lower Q, I think. Is that what big Q, lower Q is the same. Just haven't used lower Q here. I'm getting a call. Let me send that to voicemail. Oh, it's over there. I can't send it to voicemail. Okay. KQ over R1 squared, R1 hat plus K negative Q, because this is the negative charge, right? Over R2 squared times R2 hat. Right, that's the equation. And so this works for any point in space, right? Any P. But I'm gonna simplify it. I wanna put, to make my calculation a little easier, I wanna put the P on the x-axis and see what I get. So I'm gonna take the P from there, and in particular, I'm gonna put the P way over here on the x-axis. So that's R1, and R2 is from here. I'll draw a dotted line for R2. And I'm gonna put P on the x-axis, far away from the charges. Okay? And I'll make this x equals 0. And let's give this a separation. I think D is what I did. D. So this is at x equals 0, that's at x equals D. This is at some location x. Okay? You with me? Okay, so when I do that, put point P on x-axis, and I want to put it far away. So I want x to be much bigger than D. Right? So this x is very big compared to the dipole. Okay, if I do that, let's go ahead and put that information into my formula. So E of P, function of R, is going to be K, Q over, well, from R1 it's going to be x squared, right? Times R1, which is I hat. You guys with me? Plus, this is going to be a negative KQ. And this is going to be x minus D squared, but it's also in the I hat direction. Right? Because it's a little bit closer. Not much, but it's a little bit closer. Right? And I can simplify this. I can factor out a K and a Q and an I hat. So I get E at point P as a function of R is KQ. I factor that out. And then I'm left with a 1 over x squared minus a 1 over x minus D squared. Times an I hat. Okay, so I got one fraction minus another fraction. So how do I combine fractions? Common denominator. What's my common denominator? X squared times, yeah, x minus D squared, right? So I'm going to find the common denominator and put that together. KQ. The first term is going to need an x minus D squared, and the second term is going to need an x squared, and then my common denominator is x squared, x minus D squared times I. So I did the common denominator there. Okay, I'm going to erase my P. You know it's there, I need room for algebra. Okay, so now I want to simplify the numerator, so I got to multiply this thing out. KQ. So this becomes x squared minus 2xd plus d squared minus x squared all over x squared, x minus d squared times I hat. Okay, what cancels? The x squareds. All right, x squares cancel. So I get KQ minus 2xd plus d squared over x squared times x minus d squared times I hat. What was that? The x squared is canceled, right? But I saw the d squared rather than minus 2xd squared. Now I want to use this. X is much bigger than D. What does that mean? Much bigger than D. Not bigger than, it's not X is greater than D, it's much greater, which means what?
X minus D is going to be
Maybe about X.
It's gonna be about x minus d, because d I can ignore compared to x. So x minus d is gonna be x, right? So in this term here, x minus d, I could treat that as x, right? And then up here, let's think about this. Think about this d squared term versus that term. D is much smaller than x, right? So x times d is a lot bigger than d squared, right? Because d is tiny. So I can ignore this d squared, and I can ignore that d there.
Just because it's small?
Because it's much smaller.
Okay.
Not small, like little, like a lot.
Just because you're putting p at infinity.
I'm putting p far away. Yeah, not quite infinity, close. An example here is your water bottle, right? Deal's water bottle.
Mhm.
The size of the water molecule is pretty small compared to the distance between me and the bottle. That's what I'm talking about. Right, we're talking about like 10 to the minus 9 meters versus, you know, 1.5 meters or something. Right? That's the comparison we're doing. So I can ignore them. So I get E as a function of P, and this is for the dipole, becomes, I got a KQ and minus 2xd divided by x squared times x squared, which is x to the what? Fourth, right? Times I hat. And I'm running out of space. That simplifies, one of the x cancels. So I get a minus,
Minus K2D.
yeah, I have a 2 KQD. 2KQD over x cubed times I hat. Now if I plot E versus, for a dipole, what do I get? Let me turn this off. We don't need that on anymore. This is R, this is E. E for a dipole is 1 over R cubed. This is a dipole. And 1 over R squared is for a single charge. And that doesn't seem like a big difference, but it's a huge difference. If instead of Dio bringing a bottle of water, let's say he had the same amount of just hydrogen without any electrons on it, right? That positive charge would be so strong, it would pull the electrons off our body and we would be dead. But because he brought dipoles in, and it's a 1 over R cubed, we're safe. So you can see there's a big difference between 1 over R squared and 1 over R cubed in terms of the strength.
So if this bottle was all
If it was
about
pure, if you remove
hydrogen,
all the
hydrogen.
hydrogen, just hydrogen with no electrons at all,
But this small, just this size,
it would, yeah, the electric field would be huge.
it would kill all of us.
It would kill us.
Are there like
Jesus
hydrogen
Christ.
in existence that don't have?
Yeah, but they usually join up with oxygen or hydrogen itself, usually have H2,
Yeah, H2O.
right? And then they form and everything's happy.
So-
And maybe you got a couple hydrogens floating around, but you don't have a whole bottle's worth of hydrogens floating around.
So there's no way possible this is gonna be only hydrogen.
No, it would be pure
Not even-
hydrogen with no electrons.
Yeah,
Not
even
hydrogen gas.
Not even if it's like a vacuum in here.
The electric field would be huge. It would be
Has
bad.
anybody ever tried that?
I don't think so. 'Cause that sounds
Is it like a bomb or no?
dangerous.
It's not a bomb.
I mean, it would, because now you'd have all those charges wanting to repel each other.
Yeah.
So they'd all like try to explode out.
Yeah.
So it would be disastrous for us.
Isn't it the hydrogen bomb?
What
No,
is
that's
it?
different. A hydrogen bomb is when you take hydrogen, smash them together on the atomic level and make helium.
Like a huge explosion, right?
Yeah, and then you get a huge amount of
way worse
gamma
than the
radiation.
nuclear bomb. Way worse.
Then the uranium bomb.
Yeah.
Have you ever tried that?
Oh yeah, that's
Oh, yeah.
that's the modern nuclear warheads are hydrogen.
The US has that.
That's what everybody has.
Well, not everybody.
Everybody has them now.
Everybody has that.
Russia and we have them. A lot of places just have uranium.
Nuclear bomb.
That's the modern. That's the H bomb, the modern nuclear bomb.
Yeah.
Modern.
Yeah.
Probably
Get
China
out
too.
more.
Yeah, you need to get out.
Yes.
Anyway, so This stuff is really interesting. I think we just touched on it a little bit today. On Friday, we're gonna now look at taking a bar of charge and see what happens, right? If I have a bar of positive charge, what kind of electric field do I get? Or a ring of positive charge, and we get to do calculus. So exciting.
What would this look like in 2 directions?
Yeah, in 2 directions. There is a simulator for it, I think.
Because I know we had talked about like doing both the X and Y axes.
Yeah, it gets messy.
Are we gonna do that?
No, because it gets really.
Really messy.
Are we gonna have to do that in homework?
I don't think so. Not at this point.
Okay.
Oh, here's a 3D one. Let me turn this on so you can see it. This will show us a 3D picture. Don't erase, don't erase.
Don't worry.
Display. It's coming on, it's coming on. Full screen version, there it is, okay. Display field. So there is a positive charge. The whiter is more strong, and then as you get to green, it gets weaker. Yes?
Are they like randomly arrayed, these like charge things?
They would
Or
be-
does it not really?
It would be equally spaced.
Okay, it's just depicting
It's just depicting, right?
what's there.
Yes. It's just showing you a sample of the field lines. Equally spaced. There's more field lines, but it's just showing you a sample. So you can change the, you can see more of them if you, but then you can't really see what's going on, right? So that's a point charge. Let's try a dipole. There's a dipole pattern. Right?
It looks like spiders.
Yeah, it's pretty cool.
So is it better to think of them as like circles rather than like the lines? Like it's almost like a sphere around that.
Well, but the charges, they follow, like if you put a test charge, it's gonna follow the line. So it's got a direction with it. So when you drop a test charge down, because it's so small, it would end up following that line. So showing the direction the force is going. Question?
Is that how it works in like real life? They follow the line, or is that just like illustrate for us?
Yeah, no, I mean,
But if there's not like really lines,
Yeah.
there's not really, I mean, there's electric field, there's not,
they're just following the path.
yeah,
This is just the best way to like show it.
yeah,
Is it for quantum physics or no?
not yet,
Not yet.
not yet. Eventually we would, no, this is not quantum, this is classical physics.
Class.
So here is a line. So this is a positive straight line of charge. So you see that yellow thing going through the middle? If you just had a thin line of positive charges, this is the field pattern you would get. Okay. So that's from the side, from the front, it looks like that. Okay, so all kinds of cool ones on here. A plane. If I had an infinite plane of positive charge, then I get straight lines. A charged sphere next to a point charge, so it's kind of cool. Sphere charge, so you can make the sphere positive. There's some really cool things you can do. Right? So we're just getting started on this stuff. Okay.
When is the rest of this stuff? Is this like a classical mechanics thing, or is this a electrical circuit?
This is going to go into electrical circuits eventually. So right now we're dealing with electrostatics, and then we're going to worry about charges moving later, and that's when we get to circuits. So circuits.
Like our little thermodynamics intro is continued in thermodynamics.
Yeah, this would be continued in electricity and magnetism,
Okay.
and then circuits would be continued in circuits.
What's written at the top there? That equals to
Negative 2.
KQD, and QD is an interesting quantity. QD. I had that thing. That's called the dipole moment. Usually you give it a P vector. So you're going to talk about dipole moment in chemistry. When you talk about the dipole moment, it's the Q times the separation of the dipole.
And that's the one
Oh, that's just what the dipole. So this, you could write as minus 2k times the dipole moment over x cubed. So when you hear that in chemistry, dipole moment, that's what they're talking about. The charge times the separation. And it's a little vector. So, points in the direction of the dipole.
And that would kind of like take out the whole I-hat thing.
Yeah, that includes the I-hat. So it's a vector quantity, the size of the charge and the separation between them, and it points in the direction of D. So you could write it as QD vector and get rid of the I-hat. That was just for the X direction. Like that.
Could you explain really quick how magnets relate to this, like the attraction of magnets?
Not really quick,
Not really quick.
no. no.
Is it complex?
Magnetism's a whole different thing. So we're gonna get there. Let's say before we get there.
Wait, I thought magnetism was
Magnetism is related to charges, comes from charges, but it's different. And we're gonna get there. We will get there eventually, but you need to learn a lot more before I start that process. All right, turn it off. I'll see you guys.